then the sidewalk is wet is logically equivalent to if the sidewalk is not wet, then it is not raining. So that's what we're going to actually prove. So we're going to prove, let's see, not B would be if A is not row equivalent to the identity, then A is not invertible. Okay, so in other words, so to show if A is not row equivalent to the identity, then A is not invertible, right? And we realized this when we talked about this during the algorithm. We said, okay, you start doing the algorithm and you row reduce, and you realize that the whole point of the algorithm is you were starting with A and I, and we had all these elementary row operations, and you keep going, and the whole point is you want this to be the identity at the end, and then at the same time, okay, I didn't give myself very much space. We were doing the same thing to the identity. But the problem is that if at some point this is not equal to the identity, then that actually says you can't invert it. So let's just say again, this was the algorithm. This comes for free by algorithm. Okay, so hopefully you realize that A being invertible is equivalent to being row equivalent to the identity. Okay, so what about the other thing? So next thing I want to actually show is B and C are equivalent. So B says that A is row equivalent to the identity. C says that A has n pivots. Okay, so we're going to first show B implies C. So if A is row equivalent to the identity, then, well, what happens? If you're row equivalent to the identity, then you look like this, and yeah, you got n pivots. Here they are. You have, then A has n pivots, and we are done. So B implies C is super, super easy. And then converse would be to show if you have n pivots, then you're row equivalent to the identity. So, say A has n pivots. Okay, so remember, A is n by n, right? And the only way you can have something having n pivots is exactly that those n pivots are exactly on the diagonal, and then you put this in row reduced echelon. Everything else is are zeros. So that actually says that thus A is row equivalent to the identity. Okay, so that one's super, super easy. So now at this point, we actually know that the first three statements are the same, that being invertible is the same thing if you're row equivalent to the identity, is the same thing as if you have n pivots. And so any questions on any of that? Or is that okay? Everybody's with me? Okay, super. Okay. Next thing, let's actually show G, H, and I are the same. So G, H, and I. So what is G? AX equals B has at least one solution when you give any B in the target space. The columns, H says the columns span n-dimensional space. I says the map, when you take a vector and take A times that vector, is on to. All right, so let's start assuming G. So actually, I should point out that really what I'm going to prove here is that H is equivalent to I is equivalent to G. That's sort of an easier way to do things. So let's assume G. So G says that this map, so G says that if you give me that if you look at the map, we have X mapped to A times X is onto, right? Because what does G says? It says, you give me a B, vector B in the target space, I can find a vector X that maps to that. So that's just another way of saying you're onto. But then we've actually seen that if you're onto, that is exactly what I says. I says the map is onto. So thus, so I should really say this is the definition of onto. So G is the definition of onto. Just like your quiz. So G and I are the same. All right. Now the next thing we want to show is, so let's see, so where are we? H, the column span n-dimensional space. Now remember, that was one of the things we showed that was equivalent to being onto. So we were already proved that. So we already proved that if you have T of X is equal to A times X, where A is the matrix representation, this is onto, is equivalent to columns of A span n-dimensional space. Whoop. So thus, we have H, which is the column span, is the same thing as I. So H is the same as I is the same as G, so G, H, and I are all the same. Okay, so we're done. G, H, and I are all the same. Okay, so we're done with that. All right, next thing. Now we want to show D, E, and F are the same. So let me leave out my theorem. Okay, so next, D, E, and F. We're not yet into my favorite part of this proof yet. I'll tell you when we're there. So let's see. So D, E, and F, it is what it is. Okay, D, E, and F. So D says AX equals 0 only has one solution. E says the columns are linear. So this says that AX equals 0 only has solution X equals 0. Let's see. E says columns are linearly independent. Columns of A linearly independent. And F says the map X to AX is 1-to-1. So I leave this to you as a class. Is this true? Are these three things the same? Yes or no? Do we know this already, or do we have to prove it from scratch?
Hadn't we proved this earlier?
Oh yeah, remember when I was outside my backyard? We proved this, the long bloody details. We did it all. Yeah, so we already proved this. So we're happy about this. We already proved this. Great. So that these are the same. This was 2 theorems we had proven. Okay, so that's good. So now we're in the situation, let's see, where are we? So we have A, B, and C are the same, D, E, F are the same, and G, H, I are the same. So let's go back to the map. So we have, okay, so what I'm going to next prove is that A implies J. So let's do that. So that's going to be our next thing. Then after that, we're going to show A implies K. And then after that, I'm going to show, let's see, we'll show J implies D. And then we're going to show C and D are the same. So that's going to be, we're going to show these two are the same. And then we're going to show, because we got to connect everything up. C and G are going to be the same, just so you can see like where we're going. And then at that point, A through J are going to be the same. And then we're going to show that L, we can loop it into there. So this is the plan. So let's go forward and do this. So I think this part is super fun. I think this gets into the fun stuff. So okay. At least I think they're fun because they're easy. Okay, so let's see. We want to show that A implies J. So remember, A says that the matrix A is invertible. And what does J say? J says what? J says, oh, that there exists a matrix B with B times A is the identity. Is that what this is? Yeah. Okay. So let's suppose A is invertible. So let's assume A holds. So in other words, what do we have? If A is invertible, we have this matrix sitting around A inverse. So then we have what? So do we have a matrix? When we multiply A on the left, we get the identity? And you say, yeah, this is dumb. It's the inverse of A. Hooray, we're done. So you say, this is B. So it was as easy as that. So this condition here is saying that A has a left inverse. So, and we say, yeah, of course it does. We're told A is invertible, it has an inverse. Okay, so now let's show A implies K. So K actually says that there exists a matrix. So this backwards E in math, we write this also for there exists. It's a fast way to say it. There exists a matrix C with A times C is the identity. So this is called a right-hand inverse. Right-hand inverse. And again, it's as easy as can be because you say, oh, well, A is invertible. So since A is invertible, what do we know? You say, sure, I can find a matrix that when you multiply on the right, you get the identity, namely the inverse. Here it is. This is C. Okay? And in fact, I want to prove something more. So in fact, that if you can find matrices B and C with B times A equals A times C is the identity, then it turns out that B and C have to be the same. So this is actually pretty important. If you have a square matrix and you have a left inverse and you have a right inverse, it turns out they're the same. And I should just say a big warning. So warning, this is very false for rectangular matrices in general. So I should say non-square matrices. We usually don't talk about this so much in this class, but just so you realize that when you have a matrix that you want to, you can talk about having like a rectangular matrix, and then let's say this is, I don't know, 2 by 10, and then this would have to be a 10 by 2, and then you would get a little 2 by 2 matrix here, and you hope it's the identity. And you can do that sometimes, or conversely, um, uh, or if you had this matrix and you put it over here, 2 by 10, and then the question is, can I find a 10 by 2 where I get a 10 by 10 identity? So this is a fun thing to think about. Can we actually do this? But you can already see that if you start with some matrix, let me just say like this is my big starting matrix here, M, M. You can already see that that if you have a matrix, it seems unlikely that it'll work on both sides like this. I mean, you could try out something smaller, like 2 by 3, and you'll see that things are very, 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 very different, I should say, how they're behaving. But anyway, let's continue with this. All right, so let's suppose, say we have matrices B and C with what is it? B is on the left. BA is the same thing as A times C is the identity. So B acts like an identity on the left, C acts like an identity on the right. So let's actually start with this. So we want to show B and C are the same thing. So let's just have B times, so we have B times A is the identity, that's given. There's not too much we can do, but let's actually multiply both sides on the right by C, right? So this is a good technique. You say, okay, I don't really know what to do, but let's just multiply both sides on the right by C. So if we do that, on the right-hand side, we have the identity times C. So that's just going to be equal to C. And then on the left-hand side, what I'm going to do is I'm going to use associativity. By associativity, I can rewrite this as the matrix B times AC. So I haven't really done very much. But now here's the key step. We're told at the beginning that C is a right inverse. So I actually know here that A times C is the identity. So this is B times I, the identity. But any matrix times the identity is B. So we've actually shown that B and C are the same. Okay? So this is a very nice thing. And like if you take other classes, if you take a group theory class, abstract algebra class, this is a very basic thing in mathematics, that if you have an element that has a right inverse and a left inverse, that they actually have to be the same. So any question about this? All right. So the next thing I want to show is J implies D. So what was J? So J is the having a left inverse. D says, oh, AX equals 0 only has the solution 0. So now we're going to do J implies D. All right. So this is the situation we're given. B times A is the identity. And then to show D, which is AX equals 0, only has solution X equals 0. Okay, so we want to solve this. So what can we do with this matrix equation? Any ideas out there? I'll leave it to the floor. Any ideas how we're going to solve this? We don't know too much. All we know is that if we take the matrix B, multiply it in the left by A, we get the identity. Any ideas what we should do with this equation?
So if you augment the identity matrix with zeros on the right, then basically each and every variable is equal to 0.
That's correct. Okay. Yeah, so I sort of see where you're going, Paul, on this, that there is a way you could do it following that line of thinking. I want to do something that's super easy. Is there anything I can multiply this equation by to simplify it? I want to solve for x. I mean, if this was 2 times x equals 0, you would divide both sides by 2.
You can just multiply by the inverse of A on the left-hand side.
That's right. But what do we know? We, as Brennan says, we have an inverse. We're told that we have this matrix B. So let's actually do that. So let's multiply on the left by B. And when we do that, we have B times AX. That's on the left. And on the right is B times 0 vector. Okay, so now let's actually use, again, associativity. And we say, okay, that's the same thing as first multiply the matrix B and A together, then multiply it by the vector X. So, okay, so let's look at the right-hand side. What is any matrix times a column vector of zeros? What does that give us?
0 vector.
Yeah, so I didn't see who said that. It was too fast because it lights up my screen fast. And it's okay, yeah, so if you have a matrix times a 0 vector, this is just taking a linear combination of 0 times first row, 0 times the second, 0 times the nth. So we just get the 0 vector. All right, going back to left-hand side, we're told B times A is the identity. So we're in very good shape. And now what is the identity matrix times X, a vector X? If you have to write it out, that makes you feel better. Right? It is what you think it is. So it's going to be x1 times the first column vector, x2 times the second column vector, etc. Another way to say this, you actually just get the same column vector back, right? And we know that the identity doesn't change anything. So we actually solved this. What did we find out? We found out that cowabunga, x equals 0. That's the thing we were trying to show. So this is D. Okay, so this technique about multiplying on the right or left by a matrix, this is a very good one to know. I mean, this is super useful. Any questions on this? Okay, no questions. Let's see. Okay, so we're running out of time. I have like 1 minute left, thanks to my glitch this morning. Maybe what I'll do for, yeah. So maybe what I'll do, because we lost some time this morning, is, well, I'll just continue with this next time. I mean, we're actually in pretty good shape, time-wise for the class. So let me just say, next time, we'll continue with this. We have a few more of these to go, not too much. It's better if I do it live. Okay, so something I should point out is that this afternoon, I will actually post a review for your exam 1. So I'll post exam 1 review. So, and you'll see questions on there. And so what I basically did is I take your book. I mean, this is a good way to review for the exam. You take your book, you look at the sections, and you say, okay, section 1.1, solving a system of equations. Do I know what a system of equations is? Do I remember how to do that? We spoke about algebraic versus geometric solutions. So if you forget a section, you probably have to reread it, do some more homework problems, whatever, so that's, and then I just took each section and I just gave some problems for each, just to get your brains going on them, and that should help you a lot for reviewing. But again, I'll post that and I'll send an email to everybody saying that it is posted. Any questions on anything before we go for today? Thank you for being patient. I'm so sorry that my posting wasn't working.
I have a question.
Yes, Lewis. Yeah.
So is it gonna be questions and answers or just the questions?
Excellent. Oh, you talked about for the review? So
Yeah.
I have questions and I will give you very brief solutions. So you should definitely try to do it. Sit down and do it. Have your books open, your notes open, and but I will give solutions. Yeah.
Oh, awesome.
That's right. And then if you're stuck on things, you could always I can always get the teaching assistant, to hold a review session. I could always have her also tape it too, if that's useful. Any other questions?
Also, I was trying to find the recording for last Friday lecture and I couldn't find it.
Oh, it should be posted. I did actually post it this weekend. So I'll take a look.
Awesome.
But it should be there, Lewis. If not, send me an email, please, because I did post it and I always check it and it should have done it. But sometimes I have to like reload the page and then it'll show it. So, okay. All right,
Could
everybody.
you,
Oh, yeah, go
Professor
ahead,
Reddy,
Grace.
could you
Yes.
also post your written notes from today where it wasn't recording the first part?
Okay,
so that I can read
that's a
them?
great suggestion. Okay, I will do that, Grace. No problem.
Thank
And
you.
if I forget, send me an email. So,
Sounds good. Thank you so much.
okay, thanks everybody. You take care. See you Wednesday. Okay, let's see. And I should stop recording. Okay.